Welcome back to Plasma Pro Tips, a series crafted to boost your skills with ICP-OES and ICP-MS systems with short, practical advice. The nebulizer is one of the most critical components of your ICP, often referred to as the bottleneck of the sample introduction system. In today's class, we will cover the effects of operating parameters on nebulization efficiency and overall analytical performance.
Let's get started and transform your ICP from standard to superior by focusing on nebulizer selection, optimizing operating conditions, and a deep dive into how the quality of your aerosol affects the analytical performance of your ICP. Before we go any further with nebulizer operating conditions, let's briefly discuss the basics of aerosol generation and introduce some common terminology used in evaluating aerosol quality. The primary aerosol is produced by the nebulizer, formed by breaking up the liquid sample into droplets by interaction with a high-velocity gas. The tertiary aerosol is the aerosol that exits the spray chamber and what is introduced to the plasma by way of the torch. The spray chamber's role is to isolate this tertiary aerosol by filtering out the droplets that are too large, which becomes the sample waste. If these larger droplets were to exit the spray chamber and enter the plasma, they can cause plasma stability issues or even extinguish the plasma if it becomes too overloaded with sample aerosol. The transport efficiency of your nebulizer is commonly measured by the percent cumulative volume of droplets produced that are less than 10 microns in diameter. This can also be called the fine droplet fraction, or FDF. The smaller and more uniform the tertiary aerosol is, the more robust the plasma will be, and as a result, the quality of your aerosol is proportional to the quality of your results. The first step is selecting the best nebulizer model, which requires a review of your method requirements, sample matrix for chemical compatibility, and tolerance to particulates and total dissolved solids. As you can see in this table, there are many nebulizers available to pick from, so it's important to match your nebulizer to your sample matrix and analysis requirements. This detailed nebulizer resource guide, organized by the Glass Expansion team, includes everything you need to know about nebulizers, including today's topic, operating conditions, in addition to selection, maintenance, and much more. You can scan the QR code or visit the Glass Expansion ICP Resource Hub to download your own copy. The nomenclature of Glass Expansion's nebulizer part numbers provides helpful information with regards to what model the nebulizer is, the instrument compatibility, and what the recommended optimum nebulizer gas flow and sample uptake rates are. All of Glass Expansion's concentric nebulizer designs will self-aspirate at a nominal argon gas flow rate, pressurized to 40 psi. This is equivalent to 276 kPa and 2.76 bar, which are other commonly used units in instrument software. The self-aspiration rate is indicated by the nebulizer part number. This rate is standardized using deionized water. However, the actual uptake depends on the viscosity of the sample, the length and inner diameter of the nebulizer sample tubing, the sample to nebulizer height difference, and the nebulizer gas flow rate. The top table shows approximate percentage reduction in water uptake using different internal diameters of nebulizer sample tubing. The highlighted row indicates the standard packaged configuration. The most common method for sample delivery with modern ICP instruments is using a peristaltic pump or a high-precision syringe drive. When selecting a nebulizer model, choose one that matches your sample flow rate range. Our top models include the 2 and 1 milliliter per minute for ICP-OES and the 0.4 milliliter per minute for ICP-MS. For sample delivery by peristaltic pump or syringe drive, the recommended sample flow rate range for each nebulizer example is shown in the lower table. These recommended ranges apply to all of Glass Expansion's 2, 1, and 0.4 milliliter per minute concentric nebulizer models. It is acceptable to rinse and uptake at much higher flow rates for short periods, but it is important to allow enough stabilization time for the flow rate and nebulization efficiency to return to normal measurement conditions. This ensures good short-term RSDs for replicates. If the first replicate of your sample always seems to be the outlier, it's an indication that more stabilization time is necessary. To help with your nebulizer selection process, let's take a look at the quality of the primary aerosol produced by 3 different nebulizer models: a V-groove, large-bore concentric, and a high-efficiency concentric. We have kept the nebulizer gas flow constant at 0.7 liters per minute and investigated the aerosol quality produced at a high and low sample flow rate. Remember, the efficiency or sensitivity of the nebulizer is measured by the percent cumulative volume of droplets produced that are less than 10 microns in diameter. Evaluating these results, we can conclude that the V-groove would be the least sensitive and the high-efficiency concentric is the most sensitive. Both concentric designs also show an increase in the percent volume of droplets 10 microns or less at the lower sample flow rate. This is an important result. It highlights the importance of optimizing the sample flow rate to improve your analytical results. A lower sample flow rate will often translate to better precision, stability, and matrix tolerance. Next, we will examine the relationship between nebulizer gas flow rate and nebulizer back pressure. This will help us to have a better understanding of why it is important to optimize the nebulizer gas flow rate. Later, we will evaluate how nebulizer gas flow rate affects the quality of the aerosol. Using a 1 liter per minute high-efficiency concentric nebulizer, the nebulizer back pressure was measured at a range of gas flows from 0.5 to 1 liter per minute. As we would expect, the optimum back pressure of 40 psi was achieved at 1 liter per minute, which, as we discussed earlier, is also reflected in the glass expansion product number. Now we will use the same 1 liter per minute high-efficiency concentric nebulizer and evaluate the quality of the primary aerosol produced at a range of nebulizer gas flow rates while keeping the sample flow rate constant at 0.4 milliliters per minute. The trend shows us that the cumulative volume of droplets less than 10 microns increases as the nebulizer gas flow rate is increased, and thus the efficiency of the nebulizer increases. Similar to sample flow rate, it is important to optimize the nebulizer gas flow rate, and the gas flow setting should be close to the recommended value for optimal nebulizer performance. Operating at too low of a gas flow will create larger droplets and possible sputtering, which leads to a decrease in the overall sensitivity and stability of the measurements. Optimal nebulizer back pressure with a glass expansion nebulizer should be approximately 40 psi. When optimizing your nebulizer operating conditions for ICP-OES, we need to examine a variety of wavelengths. Depending on the plasma power and nebulizer operating conditions, the plasma may be better optimized for one over the other. For example, some analytes have high ionization potentials, such as the ionic lines of magnesium, zinc, and cadmium, which require more energy for ionization. Others, such as the atomic lines of magnesium, lithium, and sodium, have a much lower excitation energy and are more sensitive to changes in nebulizer gas flow. If we increase the nebulizer gas flow too much, the intensity of the elements with high ionization potential will drop sharply because the sample is moving through the induction zone of the plasma too fast to be fully excited. The best indicator of analytical detectability for ICP-OES using a solid-state detector is the relative sensitivity and relative signal-to-root background ratio, SRBR. For ICP-MS, we will similarly use a tune solution that consists of a low-mass, mid-mass, and high-mass element to monitor the sensitivity during nebulizer tuning. Lithium, beryllium, magnesium, cobalt, indium, lead, and uranium are typically the benchmark elements used. In addition to monitoring the sensitivity, we need to minimize unwanted interferences formed by oxides and polyatomic ions. To control these interferences, we monitor the cerium oxide ratio. This ratio is used to measure the robustness of the plasma. Ideally, we want the cerium oxide ratio to be less than 2% for routine analysis and less than 1% for high performance. Tuning the nebulizer, specifically the nebulizer gas flow, is the most critical step in this process. And that brings us to the recap of today's class. Today we learned some great tips on why it's important to optimize our nebulizer operating conditions for obtaining the most efficient transport of the fine aerosol droplet fraction. We learned about primary and tertiary aerosol and how the quality of aerosol affects nebulizer performance. We reviewed the glass expansion nebulizer product number nomenclature and how the product number can provide analysts with a great starting point for sample and gas flow rates, and the ideal back pressure should be approximately 40 psi. We showed that the design of nebulizer also affects the quality of the aerosol, and that a high-efficiency concentric nebulizer, like the sea spray or micromist, produced the highest volume of droplets smaller than 10 microns. This particular characteristic is what makes the sea spray and micromist world-renowned for their excellent sensitivity. And finally, we just discussed the importance of optimizing your nebulizer operating parameters, in particularly the nebulizer gas flow rate for ICP-OES and ICP-MS using a multi-element tuning solution to ensure optimal analytical performance.
Thanks, Plasma Professor. And thanks to everyone for joining. We look forward to seeing you next time. And don't forget to submit your questions to the suggestion box. Until then, happy analyzing!